For this exercise, we are going to go through this 10A class activity and we'll make some trend lines. We'll start off with Olivia's car. This is from the reading example. And we're going to plot it out first. So select your output variable, go to insert, and then you want to make a scatter plot. Move that over here. And those are your Y values. But you want to add the X values. There's a couple ways you can do that. One is if you right click, you can do select data. And let's edit this. And here are the X values where you can pick that. I'll show you how to do an easier way to do that, a quicker way to do that after as you go through this exercise. We have E and F. So now we have, let's go ahead and label this graph. We delete these extra lines that aren't needed. I go up to chart design, add chart element. It's a primary horizontal, primary vertical, and we'll label these. This one is the age of car, the X value, and the Y value that we're mapping to is the sale price. And fill out this box where it goes. Next step is to add a trend line. In our class, we've discussed a few different types of formulas that we can do, and we'll show what each of these look like. You click the data, so now you'll see that they're all selected. When you right click, go down to add trend line. I think that's command something on a Mac. And you have these options over here. Let's click on the display equation on the chart. That's our equation. And the R squared value on a chart. The R squared it's a measurement in statistics as to how well this line fits. It's created by it's minimizing the square difference between each of these dots and the line. Closer to one you get, the better the fit the model is. There are much better ways in model selection that better techniques you can use, but for this class, at a 100 level class, I think that would be sufficient. So we have these different model types that you can pick from. There's a linear model. That's a form of mx plus b. The quadratic equation is a polynomial order 2. That's ax squared plus bx plus c. And there's also the power equation. But some trend lines aren't able to do that. And so in this case, we won't use that one. You can use one of these other things as long as it will create a function, for example, an exponential that is e raised to, it's a form of a times e raised to bx. We didn't really talk about that in class, but you can use that if you want to. And the moving average, that's not something that you can really do a model, so just skip that one. Let's look at these. This polynomial, that looks like it had a really close fit. And so I think we'll go ahead and use that one. See R squared? Well, let's see. 987. That's even better fit, but let's use polynomial because that's what we're familiar with in class. So now we have this mapped out, and there's a couple of equations on here. I'm just going to copy the function right here from the graph. And it's asking the estimated sale price of a 9-year-old Honda Civic. I'm going to put some numbers here. 9, 18. Come in here and I'll paste the function. But we have to adjust this a little bit. And so we want that A times X squared. And then I'm going to put these parentheses on here just to make sure it follows the order of operations properly. And then right here, we want to do a times X. Make sure we don't have a leading 0 here. And so that gives us a value at 9 years. Using this formula, the value would put it about 7,550. Let's take a look at this between 9 and 13. Yeah, it looks like that looks like it wouldn't be that far off. And because I have these referencing the cell next to it, I can copy that formula, paste it right here. And it's using for eight years. So at 18-year-old Honda Civic would be about $3,300. And looking at this, that's, well, okay, I guess it's sort of close based off of the data that we have. This point's a little bit lower than what you'd expect, which is why it's below the line that's used to create our function, which is why 3,200 is still a little bit lower than that, but that's gives you an approximation. Let's look at this baseball example that we have. These two brothers, Brendan and Brandon, they both love baseball, and they have a bunch of data with the win percentage and the team payroll. And so they want to see if they believe that by looking at the amount of payroll a team has, that they'll win more. So the input variable is the payroll in millions of dollars. Output variable is win percentage. Then let's go ahead and graph this out. The win percentage, that's what we're explaining. So we'll select that data, come in here, insert. Let's make this a scatter plot. So this is the data that we full Z is undo. We move this graph into here. Get rid of these extra lines. Maybe you like them, that's fine. You can keep them the way you, however you want. That's not that big of a deal. But I'll select the data, and then instead of doing a right click, select the data, you come up here. The format of this function is series, and then the first argument is the name of the series, and then you have the X variables, which I'll make a selection right here. But and then the third selection is the Y variable for the function, and then you can have multiple graphs on the same image. Let's say multiple functions on the same graph. But I want these two to match up. So you'll notice that the Y variables we selected are J29 to J58, and the ones next to it are I29. So I'm going to make this to I58. So now we have all the data graphed out here. And we'll make a trend line by right clicking, add trend line. Let's see, we can even put a power function on here. That has an R squared of about 35. That's not very good. Let's look at the quadratic equation. So that is an improvement. 4143 linear 40. Okay. When you're looking at this, if you don't want to use R squared, that's fine. But you look at where you can sort of eyeball it and see how you want to get as many of these dots as close as you can to this line. So let's go with this polynomial function, what we have here. And I'm going to add some chart design elements. Let's put some primary, put some titles on this. So this is the win percentage. And this one is the payroll. We have our function here. So I'm going to copy this. Oh, this up here. You can see it a little better. I'm going to copy this function. To here, because the next part is we're supposed to do predict the winning percentage based off of their payroll. So the Yankees, the Oakland A's were 50.7 million. That's a unit we have for this. 158.5 for the Oakland A's. I'm going to put this function in here. And I'll convert this to where it needs to be. So times that. This value squared. And then see x bx. So that's times that value. And so the Oakland A's predicted winning percentage is that. And the New York Yankees winning percentage is 88.87. Okay, the scatter plot and trend line support Brendan and Brandon's assumptions that teams with higher payroll have more wins? Well, the slope on this is positive. It's an increasing slope. And so, yeah, that would be enough to say that would work. Next question is, let's go back and, I mean, it's kind of a weak line, but that's okay. It sort of works. What kind of situation would lead Brandon and Brandon to evaluate their reasoning? Well, one question I have is, what is the average percentage? If you look at the average win is 80.9% for the wins. That is, I mean, let's see, I have it set so it shows up down here, but you can do average. So with an average win rate of 80.98%, that must be an incomplete data set because these are zero-sum games. One team wins, one team loses, and that should be right at 50%. So maybe you don't have very good data. That might be a reason why this model isn't the best model to predict the win with their team payroll. Let's look at car sales. Brianna sells cars for dealership. Her pay is based on the number of cars she sells each month. She's going to be taking a vacation, and she wants to find out the month when car sales will be slowest. And so she assumes the number of cars she sells per month will follow the same trend as the national car sales. She wants to create a trend line to predict the number of cars that are sold each month. And she assumes that last year's sales will be similar to this year's sales, which oftentimes can be the case. Input variable, we're looking at the month number to predict how many cars will be sold. Let's graph this out. Number of cars sold. Insert a scatter plot. Let's put it inside of a little box. And then let's add the month number. And from here, I'll just speed this up a little bit. Things you don't have to do, but I like to do it. Add chart elements. Let's add some axis titles. Cars sold. Month number. It's not necessarily the month. Okay, so let's add a trend line. You'll notice this trend line, when you have a linear trend line, is not going to work very well because you have this where it goes down right there. So there's what a power function. That doesn't look like it hits up very well either. It's like we were going for the quadratic for the win, polynomial order 2. We could try exponential, logarithmic. Anyways, let's go for the polynomial function. And one more thing I wanted to point out is you look at the scale on this, it goes down to 195,000. I'm going to adjust that so it's a little more realistic. I mean, oh, okay. So now Brianna is trying to figure out to use a trend line equation to find the predicted value for months 2 and 7. April is 2, September is 7. And so I'm going to grab this equation up here. 2, 7. Need everything before the equal sign. Right here, we want to do a times this squared and that times. Okay, so that gives us a number of cards that this model is predicting will be sold for those respective months. There, with this comment, I can read them better. It's about 207,000 for April, about 206,000 for September. And if you look over here to month 2, that's 200. That's a little bit lower than what the model shows. Month 7, a little bit higher, but you'll notice that these dots are a little bit above or below the line. And so it looks like that's what we would expect. Make an informed decision. compute the vertex of this equation. So the vertex is negative b over 2a. So that is negative b. Here's the b. Equals negative b. And then let's put the a. I'm just going to copy this from this formula that we have. Control C divided by 2 times a value. And so we get month 4.836. And according to this, so that's right before the end of June. So that might be a good time when she can take a vacation, if that's what she's basing it off of. And right here we have evaluate your reasoning. What other reasons should Brianna consider other than potential car sales when deciding the month for vacation? Well, if she looks back and she realizes that where she lives might be different than the national average number of car sales, because you do have some variation based off where you live, and the seasonal variation may be different for that area. Or the people she sells most of her cars to, maybe ones that like to buy cars during the summer because of a specific demographic or whatever, that who she can best cater to. There's a few reasons why she may want to reconsider using this model, not using the results of this model to predict when she should take her vacation. And she can look at how many cars she sold and then model that out. And that might even better help her make a decision than what everybody in the whole country sells their cars for. Okay, next one, let's look at the fishing permit. Miguel lives in Alaska. He's commercial fish. He's getting ready to retire. He wants to sell a permit. And there's a bunch of data as to what the average earnings are and the average permit price. And those two are pretty closely related. A permit price usually reflects the future revenue stream of what that permit can offer. The next year, Fish and Game predicts that they provide a prediction that how much fish they anticipate the commercial fleet will be able to harvest, and that can translate to dollars. And so they also predict what the price of salmon will be depending on what the market conditions are. And sometimes they're pretty close, sometimes they're off, but they are used, and you can see that in the permit price preseason. And so let's just anticipate that all information they provided is correct. So next year will be an $85,000 season. So we can use this historical data to figure out how much Miguel should market his permit for. So let's graph this out. Let's make a scatter plot of the data. So we have, let's add the X variable, 76. And it looks like there's a pretty good data set we can use here. And let's add some chart elements. And then we can make this larger so I can see it. We are mapping the average earnings onto the permit price. Let's add a trend line. And let's so if you have a linear equation, we have an R squared of about 586. That's pretty good. How about a power? That looks even better. 0.6 something. Okay, the quadratic of 5924. It's a 50%. 5896. None of these look like they're that bad, but let's use the power equation. It looks like it's probably closest. Let me grab this equation, because now you're wondering how much you should sell the permit for. Oh, there's 85,000 is a predicted season. Times x raised to that power. So using this particular model, it looks like he maybe ought to market his permit for about $130,000. That's if you're using that model. If you picked a different model, it would be whatever the model predicts. Evaluate your reason. How did you decide which type of trend line to use? How strong was the pattern for your data? I mean, it's fairly strong. You still have all these. I mean, you can see that it starts to spread out a little bit the further you go out. And so there's maybe some other confounding things that are not included in what we're graphing if you're using this type of a model. But anyways, it seems like it's okay. And then you look at 85,000, you see if we have examples of that type of revenue otherwise. So like here's one for 92,000 and the permit price was about 128,000 at that point. But you also see this one out here, 97,000, 162,000. So somewhere in that range is probably okay, maybe. I don't know. It's hard. Well, this gives you a starting point to think about where you'd want to sell your permit at what price. Okay, let's move on to the next one. We have number of cell phones, United States, 1990 to 1999. We're going to graph this out by year. Insert scatter plot. And let's move this over here. Let's put the year in there. Where are these lines? Add some chart elements. So this is year. Subscribers. Now we'll add the trend line and we can determine which trend line we want. So linear looks like has a pretty strong model. Power, well, there's a value here so close to 0, it's displayed as 0, and that's not going to be very useful when we try to graph it out. Let's not use that one. There's a polynomial and exponential. Some of these functions, well, they work really closely. You want to pay attention and pick one that actually works. Let's try this. Let's try this one right here. We have the exponential function, and I think it's not going to work very well, and I'll show you why in just a minute. It's 91 and 2000. So we'll put the function in here. This is that value. That's 6 times that's 10 to the negative 264. With a little e, it's exp. That value. Okay, that actually looks pretty good. So we have 7,540. So we look at that number in here, and 1991 right after here. Looks like that number would actually work pretty well. Put that in here. And 121 for what year was that? 2000. That seems like a pretty high number. Is it really growing that much? I mean, if you look at these last, it starts to miss a little bit, and so that might be a little bit suspect. But I mean, overall, this model works okay. But let me show you something else. If we were to change this to, say, a polynomial function, And we'll use this new function. I'll come over here. I want you to think about what these results are and see how well they track. So we have this thing in here. Times that number squared. That number times that. And so now we have this negative, I don't know what that huge number is. We'll put some comments so I can read it a little bit better. That gives us negative 16 billion or something like that. And the reason why is because when you're predicting it using this, you have there's 3 million something, and it just rounds it off. It gives a scientific notation. So you can't really see what that number is, plus 3 billion. And if you had the actual predicted values instead of just e raised to something like that, then I think you could have a much better model that can be used for prediction. But in the meantime, please don't use this one if you get results like that, because those results are completely useless. The reason why we do this modeling is so that we can make some sort of a prediction with accuracy. But so it would probably be best to go with the function that we had before, was that the exponential function, or whatever model you end up using, use one that gives you results that are useful. Okay, well, I think that's why we have the cell phone example. Lastly, we have this light example. Miley's trying to look at intensity and distance. So let's graph this out. Yeah, move this around a little bit. I'm going to add the distance in here. Okay, and then you can do things like you can change the axis. Let's see, what one of these will have axis option for this. So minimum is, let's go to 1. How about 0.9? And then the maximum here that we have here is, okay, there we go. Now it kind of shows up in here a little bit better. And let's add let's add these chart elements in here. Distance. Intensity. Okay, now we'll add our trend line. The linear looks like it kind of runs through okay, but it's too low on this end, too high on that end, too high on that end. And so let's look at some of these other ones. The power function actually looks like it tracks really well, as does, let's see, the polynomial does too. And did we try this one? Oh yeah, that was okay. That one tracks really well too. But I mean, this looks like a good model that we have right here. Let's copy the model and we'll put this in here, distance from 1.25 meters, and distance from 2.2 meters. And we times x it's -2. Oh, that doesn't look like a very good model, does it? Something went wrong. Either I set it up incorrectly or x. Oh, I know what I did. It's x raised to that power. That's the wrong character. So we have that many lumens at 1.25 meters. Let's sort of check our work too. So 1.25 meters is right between here and here. Yeah, 0.19 looks like that would fit. Looks like we have a pretty good model there that would predict what we're doing. And so great, that's everything we need for this uh, for this exercise.